Your Royal Highness, ladies and gentlemen, please give a warm welcome to Peter Phillipson.
Your Royal Highness, ladies and gentlemen, this year is 200 years of Fresnel's wave theory of light, and it's also 200 years since he realized that he had done an experiment that had already been done, and for a while he was very, very upset. And the experiment had been done in this building originally, and we're going to recreate it for you, but he did a little twist on this experiment and forged a good working relationship with the Royal Institution and brought the thing forward, and we'll see what he did. He was born in 1788, which is the same year as William Hazlitt and Lord Byron, both romantic writers, and you could say that Fresnel was a romantic scientist. In those days, there was no real distinction between an artist and a scientist. They just all believed in the Enlightenment and helping each other. Indeed, Wordsworth was a very good friend, if you go to Wordsworth's house, very good friend of Humphrey Davy, who also resided in this institution and did lots of experiments, and they just exchanged ideas all the time. Fresnel was living in Mathieu, which is a little town in Normandy, and I had the pleasure last week of meeting some representatives of the mayor of Normandy, and they had done a lot of research into his early life. Fresnel grew up in Mathieu, near Caen, in northern France, but he was born in Broye. His father was an architect and entrepreneur from Mathieu, but his mother, Augustin-Jean, who was also born in Broye, was from noble descent, and whilst his father was restoring an old house that her father owned, they met each other and became married. His uncle, who was called Leonor, educated Fresnel at the École Polytechnique when he was 16 years old. And then he went on to the École des Ponts et Chasseurs in France. He had three brothers. One was called Louis, who was a soldier who died at Jacka in Prague during a battle. His younger brother Leonor, who was an engineer and who kept lots of the ideas of his famous brother alive after his death. And his other brother Fulgence, who was an Orientalist, who translated lots of Muslim ancient texts and other architectural manuscripts. He had a notable cousin called Prosper Mérimée, who wrote lots of poetry, but was responsible for restoring and keeping alive the idea of looking after ancient monuments in France, a bit like the forerunner of the National Trust in the UK. This is the house that he grew up in. He wasn't born in it, but he grew up in it. And it had been a family home of his father's for many hundreds of years. And behind that window is where we think that he wrote most of his famous manuscripts when he was under house arrest by Napoleon. This is the roll call of the school that he attended, and you can see his name listed amongst his fellow contemporaries. And he was also a prolific drawer, and here's an early picture of a school that he worked on the design of. A lot of the scientists in France at that time were put under house arrest, and he spent his time doing scientific research. And in the space of 6 years, he produced an astonishing plethora of ideas. And what I want to do is to present some of those ideas that he did. The first thing, he noticed that there was a difference between sound waves and light waves. If we were to listen to two sound waves that were very similar frequencies, say 256 hertz and 260 hertz, about 4 hertz apart, you would hear the sound between the two. The drawing there shows that you would actually see a 4 Hertz reverberation between the two. We were going to have 2 singers to sing that for us tonight, but one that couldn't do it. But you'd get a sort of a ying sound. Now that's called beats. And you might say, why am I talking about a sound phenomena called beats when we're talking about light? Well, the thing about it is that there is no beats equivalent in lighting. The fact that the light doesn't have this effect means it tells us something about light. Because the reason the sound waves beat is because they're longitudinal. They act like a spring where the particles of air get close together and then they rarefy again. But light doesn't behave like that. So straight away it told him something that it can't be longitudinal. Some laws of reflection were already known, and laws of refraction were already known, but he added to them greatly. So let's see what was around at that time. If we look at this piece of glass and we reflect light off of it, everything in lighting has a normal, which is a right angle line, which we've marked in an N. So all the little animations that have normals have a green N, and it means that it's just a line that comes at right angles to the page. So all angles are measured from normals. And this has permeated out into lots of other subjects. What we find is that the angle of incidence equals the angle of reflection. And you might think that's obvious, but here's the proof of it. And it's just a bit of, it uses an idea from a couple of 100 years before that called Fermat's principle of least time. It means that the amount of time it takes light to go from A to B is it's the shortest time. And so that's a mixture of Pythagoras and Fermat's principle of least time to work out that the 2 angles are the same. The other thing, that is in fact the second law of reflection. At schools, they only teach you the second law, but the first law is this one, and it's less obvious, but it's the fact that the normal and the incident ray and the reflected ray are always in the same plane. So you could put a piece of paper and they would always line up together. And as it is with refraction, if we shine a light incident on a piece of glass, it bends, and it bends according to the wavelength of the light. And anything in science that depends on the wavelength of something is said to be dispersive. So it's called dispersion. And again, this law was known to a man called Snell before Faraday, and he worked it out using Fermat's principle of least time. And Ptolemy, 2,000 years beforehand, had tried to work this out, but he couldn't work out the fact it had anything to do with sines of angles. So it stood there in the air for quite a while. At around the same time, or just before Fresnel, was a man called Lambert, and he worked out 2 formulae that if you have something that's diffuse, like this piece of paper, the area that you see, it diminishes by the cosine of the angle you look at it, as you start looking at it from different angles. But the intensity of light hitting you at that angle drops off at the same rate as the angle does. And so wherever you look at it from, it always looks the same brightness. And this is called a Lambertian surface, a diffuse surface. And the moon is very similar to that. The moon is a bit like a perfect Lambertian surface. So wherever you look at it from, it has the same brightness. What he said was that the solid angle that that circle creates is the same in all angles. And wherever you move your eye, the angle subtended is the same and the light drops off the same way. So Lambert, in fact, wrote some lovely books, And these are some original books from his time. I'm not going to open them fully because it would break the back. But these are beautiful, original pieces. And he was the person who worked out that pi was an irrational number. He started off as a mathematician, and he was the person that worked out that you can't write it as a fraction between two whole numbers. It does, in fact, have an infinitesimally long number. And as a result of that, it turns out that the light hitting at Lambertian surface to the light reflecting off it is pi. So as well as being the ratio of the circumference of a circle to its diameter, it's also the ratio of how light strikes a diffuse wall like this and comes off it again. That's also pi. We're going to do an experiment now. This is called Young's two-slit experiment. It was first done by Thomas Young in this building in 1801 and 1802. And Fresnel didn't know about Young at the time, and he did this experiment in 1814, slightly differently. And this was the experiment that he was disappointed to find out had already been done. But it's very important that we know the essential point of this, because this is what made the wave theory of light that we've come here to talk about. Now, Bryson Gore, who's going to come out here, who's very well known to the Royal Institution and on television doing lots of experiments, he's going to perform the experiment with us. And most of the equipment is over there because the path length has to be long. And we've got a roving cameraman called Rob, who's going to zoom in on any piece of equipment so you can all see it, even if it's out of sight. So then, if you'd like to...
Thank you, Peter.
Tell us the essential part.
Yes, okay. This being a demonstration performed here by Young is one of our favourites at the Royal Institution. Originally performed with naked flames or sunlight or the like, rather difficult to do, most of them being quite weak. We're using a modern laser beam, which is, as Peter says, down the corridor, which is shining a beam of light across the room onto this screen here. And if we look at the screen up above, Rob's camera is showing you a red dot. Well, it's not quite a dot. Were it just travelling through the air, it would be a perfect circle of approximately the height of the blob that you can see on the screen. But we're passing that circular beam through a vertical slit. Now, if the slit were wide and we begin to narrow it, it does exactly what you'd imagine. It acts as an aperture and cuts off the edge. But the surprising thing that Young discovered was that when that slit gets to the order of 1 millimetre across or less, instead of making the beam of light narrower, it begins to spread out. The slit we have is about 0.5 millimetre wide, and you can see that it's spread the circular spot out into a strip maybe 4 times wider than it is high. That's the passage of light through a single slit, forgive me. What I'm going to do now is open up a second slit just 1 millimetre to the right of the first. That second slit will make another patch of light almost identical to that, but offset ever so slightly. So what we'll produce is 2 patches of light, one on top of the other. When Young performed this experiment, the expectation was that you would see twice the brightness of light, if I've got this correctly set up. What in fact he saw was this. The 2 patches of light created narrow bands of light and dark. So the 2 most important features of Young's double slit. A slit, once below approximately 1 millimetre, begins to spread a beam out the narrower it gets, and 2 slits closely placed produce light and dark when both sets of light are on top of each other. That was a remarkable result, that light plus light could produce dark. This is what Young and ultimately Fresnel needed to explain. I would say the separation of those narrow slits, those narrow bands, depends upon the wavelength of light. It also depends upon how far apart those two slits are. But for our experiment, that shows the two primary features. Thank you, Peter.
Thank you. Now, what Fresnel then did, let's look at the analysis of this experiment. So you've got light coming through one slit first, and that is, Fresnel did lots of work on just the one slit first, and it's called diffraction. It means it spreads out. And what Young had done, he had gone with the two slits straight away, and what he was really seeing was the interference pattern between two diffraction patterns of one slit each. And that's what, if we were looked at the amplitude of the brightness of those red dots that you saw, they're very bright in the middle and they progressively get light and dark but attenuate. And then if you have two slits, you'll see that you get within them a second set of ups and downs. So that's the effect of the second slit. The way Fresnel did it that was different was, instead of having two slits, he did a prism known as a Fresnel biprism. Now, I've got one here, and if you looked at it quickly, it just looks like a flat piece of glass. But actually, in the middle, about 2 millimeters higher than the edge, there's a slight point. So there is, in fact, two very, very narrow prisms indeed. And it's called a biprism, and they're quite hard to get hold of. And this is what it looks like. So in this animation, we're going to exaggerate what it looks like. So that's what it looked like if it was too big, and then he made it a lot smaller. And as the rays of light pass through it, even though there's a single light source, S, you see two virtual light sources, S1 and S2. So if you looked through it, you would actually see two, but it's your eye-brain combination following the rays back, making you imagine that there's two. But if you were to put a screen there, there's nothing there. That's called a virtual light source. And with this virtual light source, he managed, back then with their terrible light sources of just candles and things, he managed to make a much brighter image. The only way he could explain this was to say that light was a transverse wave, and he lost a few friends over it. People like Biot, for example, he disagreed with this. And even Young himself was a bit unsure. Now, there's another thing that really nails the idea. I've got here a piece of calcite, which back in his day was called Iceland spar. And if I hold it and look at it, look through that exit sign, I see an ordinary ray of light passing straight through and seeing the exit sign, but there's also, it refracts twice, and you see a second ray. And Rob here, the cameraman, is going to show you what I've just been looking at. Now, for about 150 years, nobody could explain why this happened. And all of Fresnel's papers are in France, except one, which is at UCL, and it's called Mémoire sur la double reflection, which, if I could only say it, means there are two words for it. The double refraction is also called bifringence, and he explained bifringence when no one else could, and that really, really nails the wave theory of light being transverse for the next 80 years. So he thought a wave was like this. It propagates to the right there, but the energy was at right angles to it. This is not quite a complete story, and if Frank James is here, is he? Professor Frank James is from the Royal Institution, and he researches into the papers of Faraday. Just after Fresnel's early death, this experiment was done here at the Royal Institution, and we're going to demonstrate it now, and I wondered if Frank would come up and just say a few words about it. What we've got, just to explain, and if you would like to come and have a look, you'll give us the background in a minute. But what we've got in here is a magnet which gives out a horizontal magnetic field, and we're going to pass an electric current which is vertical and therefore at right angles to it. Ignore the mercury, it's just so that everything conducts. And if we plug it in, what you should see is that the conductor is actually rotating. And this was the first demonstration of the motor effect. And what I'd like to ask Frank James is, what was the mood music like around at that time in 1831 when this was being discovered?
Mood music in what way?
Well, I know that Faraday disagreed slightly with Fresnel. He didn't like his one of his theories to do with the ether.
Well, yes, Faraday did not like the ether one tiny bit, because to have transverse light waves, you've got to have an elastic solid ether, and Faraday didn't believe in that at all. Nor did Faraday believe in Newtonian physics of forces acting in straight lines, which is why this experiment is so important, because it shows that forces also act in curved lines, and that's the huge significance of this particular experiment. And the other thing about this experiment was that Faraday was able to say to Ampère, in his general theory of electrodynamics, had claimed to be able to explain all electrodynamic phenomena using basic mathematical principles. And Faraday said, well, you didn't predict this phenomenon, therefore your theory isn't complete. And Ampère never really recovered from that criticism. Very long set of correspondence between Ampère and Faraday in 1821, 1822, 1823.
And I also believe that Young was not an incredibly liked speaker when he was here.
Oh, no, Young was Professor of Natural Philosophy here in 1802, 1803, and in his lecture notes, which also at University College Archives, he apologises for being such a boring lecturer right at the end of his course.
Well,
Not often you see that in people's lecture notes.
Let's hope that we don't emulate that.
That's
so,
right. Okay.
Well, thank you very much.
You're welcome.
So. Right then. So if we add what's known here to what Fresnel did, we'll see that the wave that we had, the transverse wave, can actually be added to now. We're adding magnetism to it. So this wave has now become an electromagnetic wave, and you'll see that the magnetic wave is at right angles to the electric wave. They're always at right angles to each other, but as they propagate, the pair of them can rotate. And if they rotate, it's said to be unpolarized. But if you can only allow ones at certain angles to pass through, it's said to be polarized. And that's something else that Fresnel worked out. If we would like to dim the lights now, if we look at the sun, our sun, we'll find that if we could pan to the left, we wouldn't see anything, because light doesn't reflect. If there's nothing for it to reflect off of, it's invisible. We only see it when we're either looking directly into it or if there's something for it to reflect against. In fact, while I've been talking, there is a light here that's on, and you can only see it because I'm putting a thing in front of it, whereas you hadn't seen it before. But in space, it might reflect off some cloud of dust. And there we are, cloud of dust, which is scattering the light. It's a scattering phenomenon. But of course, space isn't as dark as that at all. There's all the other millions of stars in the background. So we have to put those back. So what's going on? You're getting direct light from stars and you're getting scattering. We then come to our own moon and Earth. And the light just lights it on one side only. And every now and again, we'll get an eclipse. So what will happen is the surface will turn red because the moon will be in the penumbra of the Earth, the shadow of the Earth. And if we were to look from the moon itself, we would see the sun going behind the Earth and the atmosphere turning red. So on the Earth it looks blue, but during an eclipse on the moon, if the situation is right, it will actually look red. So let's now zoom down into our own planet, into the strand. When I was young, I was walking along with my parents and I noticed how the light reflected off buildings. So you've got the scattered light of the sky, which we're going to talk about in a minute in an experiment, but direct light is still hitting the buildings. What we see is the light, as it comes down, will hit that glass panel on the left. It will reflect off towards us using the equations that we spoke earlier about. And a friend of Fresnel's called Mallius noticed this effect in the Palace of Luxembourg, and when he held up a certain glass in front of it, he found that the reflection disappeared. So he discovered that light is polarized on reflection, and the polarization is also pi, exactly the same as what Lambert have found about diffuse surface. This number pi comes up a lot in the study of light. So again, with this building here, the light will come in and we see that reflected off the window. But not all buildings are like that. If we look at the Royal Courts of Justice here and we allow the light to come in, we'll find it's reflected in all different directions, and this is diffuse reflection. If we now look at a road where it's previously been raining but it's beginning to dry out, you're getting a mixture of specular and diffuse reflection going on all the time. So if we study this a little bit, sometimes if you look at the world again, you see things that you might not have seen before. We're getting light coming off of that puddle there because it's reflecting towards us off of that white pillar. But the yellow poster behind, the light's going to hit that, and then, because it's diffuse, it's going to reflect in all directions. But that isn't the end of the story, because some of that diffuse reflection will also strike off of the puddle and become specular again. So there's this interplay between these two ideals going on all of the time. In fact, Fresnel, you could say Fresnel's take would be that watching paint dry really can be interesting. Now, if we look at this this puddle in the road, as the cars drive past, some of the car you'll see as it dries over the wet patch, but you won't see it on the dry patch because the light's being scattered differently. And this is exemplified when eventually you'll see the indicator light and stop light at the back of a vehicle going over the puddle, and you'll see a part of it clearly and you won't see another part of it. And that's that's showing that the angular nature of light is very, very important. And indeed, most programs like Dialux and all the simulation software have a setting on them called full Fresnel, which means they give an accurate description of the world, which is what this is, really. Lastly, we just have a quick, this is our film noir that we did in the Strand. We've adjusted the camera so that the contrast is quite high. And you can see very bright specular images. Specular means that they obey the first law of reflection, and diffuse means that they're more Lambertian. And there's a mixture going on all of the time. So all of the sheen you get off the road and the reflection off the glass on the bus as it goes past are all described really accurately by these equations. And lastly, on this part, we'll just look at a couple of vehicles going past, and you can work out where the sun is in this shot. It's a real low, early January shot. And sometimes you can be in the beam and not be able to see very well when light reflects like that. Right. Well, I was talking about the scattering that makes the sky blue, and you might say, well, that's called Rayleigh scattering. What's that got to do with Fresnel? Well, half the equation is to do with polarization, which is something Fresnel worked out, and the other half of the equation is to do with the aerosol, the size of the droplets in the atmosphere. And what another person that used to work in this building in the past took Rayleigh's work a step further, and we're going to do his experiment now. And Bryson has made a new take on it, and he's going to explain exactly what we're going to do.
Thank you, Peter. What I've got here is simple fish tank, empty with just air in. And we're shining a beam of light onto the front face of the tank. And you can see Peter's shadow perfectly in the beam of the light here. This square here is a reflection from the front face of the tank. There is then a mirror at the back face, which gives the brighter rectangle over on your left, on the left hip, sorry. I can get shadows in all of them. So the bright rectangle is from a mirror at the back. The pale, larger square is from the glass at the front. And what we can do is fill the tank with an aerosol. Tyndall had the most fabulous ways of generating toxic smokes, which I have done on occasions. But this evening, I'm going to just very simply use some soot from a paper straw. If I blow in through the straw, I can fill the tank with smoke. The smoke granules are very fine and will scatter the light. And if you're sitting to the side of the tank, you will indeed begin to see the light as it passes through the tank. If you look back at the screen, I think that should probably be enough. I'll give it one more. If you look back at the screen, you can see that the smaller rectangle has become much, much dimmer because the majority of the light is now being scattered out to the sides and up and down. But not only is it dimmer, it is distinctly redder. Now, clearly, had we used red smoke, that wouldn't be surprising. But for those of you sitting at the side, you'll see that the light coming out is blue. This very much shows that the light scattered to the side is blue. The light that travels through and is scattered very slightly is the red light. Hence the reason for a red sunset, and hence the reason for the moon turning the colour of blood, which was the biblical description of a full total eclipse. because the light that does just scatter ever so slightly round the outside of the Earth through the atmosphere is the red light, which will then strike the moon and turn it red. So, as I say, the Royal Institution, we call it Tyndall scattering, but it is a combination of Tyndall, Rayleigh, and Fresnel's mathematics.
Thank you. I've got here... I've got here a communal garden egg being boiled, and it's not quite done yet. One of the reasons was I was going to show you something to do with reflection, to do with it in a moment. And also, I've always wanted to set off a Bunsen burner at the Royal Institution. So we'll let that. It's about ready now? Okay. So we're going to put a light on from this side, just from one side. And if you would like to perhaps come...
I think if you look at the screen, you can see I'll keep taking it.
Yeah. When we first take the egg out the water, it's very hot, and because it's wet, the reflection off it is specular, but it dries out really, really fast because the surface area is so big. And what you'll find is it becomes diffuse. So very, very quickly, you're seeing the two ideals of reflection going on very quickly. So next time you make your breakfast, you can try this at home. Okay, thank you. There was a play on last year, Madame Butterfly, and it was very unusual because all the dancers performed on a mirrored surface. And what it does, normally if you have even the best painted diffuse black surface and you light it, you'll see a circle of light around the actor. But if you make them walk on glass or a metal surface, that will be reflected away. So they had this ethereal look where they were lit, but you couldn't really see any light shadows around them. And so, in a small kind of way, there are two things about this I was going to explain. The firstly is if I just light this very diffuse, perhaps we just have the lights down a moment. We've got here a matte finish, and you can see the spots of light on it. Now, it still will exist, but if we put a mirrored finish here, it's diminished, and it's very, very bright up there where it wasn't before. The people in the audience, they might just be able to see the reflection of this. And so this is just showing you the difference between the two. There's another idea I'd like to tell you about this. In America, they call torches flashlights. And there are two meanings of the word flash in lighting. One is to go on and off, where the actual source is going on and off. And the other is if it's left on and you move it around things, they reflect back at you from time to time, depending on how the light catches them. And that is also called flashing. And it's used in designing reflector systems. So anyway, this was the mirrored finish on Madame Butterfly that they were performing on. If we apply this to street lighting, you'll see this street light here, when it lights the road, it lights a patch in front of you, which is a T shape. And most people that sit in a car are about 1.2 metres off the ground, and they see a patch of road 60 metres in front of them. And the idea of the lighting is to light the road, not the cars on top of it, but the road is supposed to be glowing, and everything else is seen in silhouette against it. When we were looking at the Strand earlier, that was during the day. This is at night time when street lighting is being used. We'll see that if it's raining, the reflections off the road at the front look darker because the light reflects differently.
whereas further on, where the road is dry, it looks more diffuse.
The worst place to cross a road is near but not on a crossing, because the drivers will be looking at the crossing and will probably not see the person at all, or can flatten them without seeing them. So jaywalking is a really bad thing to do near a crossing. So. Now, this animation here, if we could turn the lights down, what you're seeing, this is a street light being viewed from the horizontal. And if you look at the numbers on the screen, the middle one is the angle at which the light is being measured from the downward vertical. And the other number is the intensity. And as we look through this photometer, I like this particular photometer because it has what's known as a Maxwell Ian View. You can take the photocell out and put a camera there, or put your eye there, and you can see why a reflector is working or it's not working. Whereas most of the photometers, they're fixed, and only machines can look at them. And I think it does you good to actually, if you're designing something, to see why it's working or not working. And you'll see the intensity has shot up, and that reflector is glowing. It's said to be evenly flashed because it's being illuminated by the lamp. And then so as you don't get a large spot of light directly underneath, that reflector will eventually go dark as we go underneath. That was taken at the Fosco photometer in Ware, where I used to work when I was younger. Okay, so when it hits the bottom, here you'll see the other reflector at the side has gone completely dark. And then what the machine would do is turn it through a few degrees and measure it the other way. Now, I'm going to show you something from the late 50s, early 60s. Harry Worth used to do a comedy show, apparently, and it started with him performing this. And here, this is pure Fresnel, because what Fresnel said was the reflection you get when you're almost grazing incidents, when you're almost at 80 degrees from the normal, is really, really high. And then as you get further in front of a piece of glass, it drops right down to about 4%. For different refractive indices, for different types of glass, you get different reflections. But you'll see with all of them that the reflection when you're almost at right angles to it is very, very low. It's still there. If it's 4% and you've got the sun behind you, 4% of sunlight is still very high, but it's much lower than it would be when we were looking at Harry Worth at that greater angle. So if we study him, we'll see him quite brightly. If we then move the camera in front, the reflection goes right down, but we will indeed see ourselves taking the pictures. Posterity has shown us that if we actually did look at what Harry was doing when he made that clip, that his leg really was actually coming off the ground.
Okay, so to summarise the reflection that we've learned, if we take a block of glass, like we have before, and we draw a normal to it, then we've got an incident ray, and that comes in at theta I to the normal. And then we've got a reflected ray, which for a specular surface equals the angle of reflection, theta r. Okay, and we know that theta I equals theta r. That was known before Fresnel. And then some of the light will be transmitted, and so it'd be bent towards the normal, and that's the transmitted ray. And then we have a refractive index, which is the ratio of the speed of light in vacuum to the speed of light in air, which is more or less 1. And then in the glass, you've got the speed of light in glass to the speed of light in air, nt. And we know that n sine I equals n sine t. And that was known before Fresnel. But what he adds is this. Some of the rays are actually in the plane of the paper. Okay? So we first consider the wave coming in the plane of the paper. So I've just drawn it in the plane. And the reflected ray equals Ni cos t minus Nt cos I over Ni cos t minus Nt cos theta I. And for the transmitted one, and this is again parallel to the paper, that equals 2Ni cos theta I all over Ni cos theta t plus Nt cos theta I. And there are two similar ones for the other ray, which is coming in and out of the page. So the ones going in and out of the page have different reflectances, and this is what Fresnel learned. This is a graphical representation of Fresnel's reflection equations. So in conclusion then, every reflection in real life falls somewhere between the two extremes of pure diffuse Lambertian reflection and pure specular Fresnel reflection. I'd like to show you now these paintings by Magritte. If you look at them quickly, they all look exactly the same. But he did in fact do about 27 versions of this painting called The Empire of Light. If you look at them quickly, they look just like an ordinary house. But what he's done and what makes them surreal is that the laws of light and how light reflects off the architecture have been distorted. So in some of them, the sky is daylight, and yet the front of the building is in shadow, as if it's nighttime. Other times, different aspects of what's going on in the painting are slightly distorted, and it's fun to look at them and compare them and see what's right and what's wrong about them. This is what would happen if Fresnel's laws weren't applicable. So normally we see the world a certain way, but what's so great about these paintings is they show what life might be like if some of his laws didn't apply. Okay, before we do our next sequence, we're going to do another experiment. If we ask Rob to pop over, we see in this goldfish bowl, all you'll see is it's a goldfish bowl with a little plastic other bowl inside it. Okay? But what Fresnel didn't know in those days was a thing called hydrogel. Okay? Sodium acrylate. If we pull it out, we'll find there are indeed little balls of this material inside. But when we put it back in, we find that it disappears again. And that's because the refractive index of both materials is the same. If you put this result into his equations, you get a 0. So even though it's 200 years later, it predicts that this would happen. And it's very good in science sometimes to take a trivial result and just test it to see that it's working correctly. So yes, this is the hydrogel. You might say, well, this is all well and good, but I'm an artist, and how does this relate? How does all this science relate to what I do? I used to have a job where I worked in the professional theatre at night and at weekends. And I worked during the day in a lighting lab, so I had a mixture of the two. And if we applied some of these science ideas to an art gallery,
what we do, if we walked into the gallery and then we pan left, we will see various paintings on the wall, okay? We'll see the scalloping of the light on the walls, and we'll decide which one we're going to go and see. Now, in this gallery, some of the paintings are glazed, but the wall is diffuse. But if we just for a moment pretend the whole wall was made of glass, you'd get a cacophony of interreflections everywhere, and it would be a mess. So if we just take that glass and take it down just to one painting again. So we've got this Van Gogh that's being glazed. And while we're looking at it from a distance, it looks fine. And then as we walk closer to it, we'll see that there's light in the way and you can't quite see what you want to see. You can't see his face very well because it hasn't been lit properly. So as we stand in front of it, some of that reflection disappears from the other wall. And then as we go closer, we'll see that what had been happening as we walked to it was that the lighting had struck the walls from like we did before. If we were to move the lighting that's lighting the paintings, we'll find that the angles at which it strikes the viewer changes, and therefore the different zones where it's good and not good to see the painting varies. So as the lights move, the angles will change. So this painting that's been lit badly, if we were to move the lighting, we could sort that out. Now, if we were to have a young child with us and we were to light the painting for an adult, the young child might still get glare. So if we then pick up the child and put it on our shoulder, they might see it clearly for the first time properly, and who knows, it might inspire them to have a go at doing some painting themselves. So what Fresnel tells us is how to light an art gallery properly. It would be a good example of it. Okay. Now, we're going to move on to our next experiment. We're going to do some studies of bubbles. Okay. Now, another thing that's to do with interference are the colours you get in bubbles. And what the bubbles are caused by a thing called thin film interference. And it's sometimes wrongly called iridescence, but it is a much nicer word. And it's the fact that the bubble is so thin that the light bounces off the front surface, refracts through the thin film, and then is reflected off the other surface, and those two beams interfere with each other. And what Bryson set up here is a massive soap bubble, and we're going to project it onto the wall here. So if you'd like to take the lights down now. What's happening here is as the soap, this is a vertical bubble, as the soap runs down under gravity, the colours go through a definite order because the thickness of the bubble at the top is a lot thinner than it is at the bottom. And if the bubble doesn't burst prematurely, if it lasts the whole length of time, and if you've got a little child's one that sits on the wand and it doesn't burst too soon, you'll find that eventually it goes completely black at the top. And when it goes black, it's only half a wavelength of yellow light thick. So it just shows you just how thin a thin film has to be. When you see oil in the road when it's been raining, the pattern doesn't last very long because it soon becomes too thick. But you'll see this colours running down, and they go through a definite order, the same order as they would go through a prism.
If I might, just from my experience, the lower half of the screen now is the thickness of the soap bubble is greater than about a micron, a thousandth of a millimetre. It's greater than one whole wavelength of light. The upper half now is, the thickness is less than, forgive me from my recollection, either 1 or 2 wavelengths of light. We are on the last patch of light. As the soap film becomes thinner than this from the top, the two faces are so close together, less than the wavelength of light, such that the reflection from front and back are interfering with each other. It does take a period of time, but I think you can begin to see a darkness forming in the top half. That is because this is becoming below the wavelength of light. The interference is destructive, and in the world of science, it's known as a black lipid layer membrane, so thin, just the thickness of the soap molecules.
And this is what is going on. If we take the soap bubble, just take the thickness of it, we'll see that the lights, some light's reflecting off the top, the rest is being refracted in, and it's destructively interfering with the first light ray. And then when it's half a wavelength of light, but you get total annihilation of the beam. Okay? Right, when you leave tonight, you'll be in Albemarle Street. As night falls, you'll notice how the light varies on the buildings. And if it's been raining, you'll find that the coldness will be felt on your face, and you'll smell the dampness on your nose. But I would also argue that if it has been raining, the light angles will be changed, and you'll notice them. It's an innate thing, you see it every time. So all of these things collude, and you can literally see the world in a different light. I'd just like to say something about the first experiment that we did, because it's been repeated in the 1990s and in the last decade, far from being a footnote to history, far from being something just from 200 years ago that we can forget about. It's totally current, and it's called quantum annihilation. And Bryson has set up an experiment where we're going to do Young's slit experiment again, but we're going to use this quantum idea that if you try and observe quanta of particles of light, if you try to observe a particular one, you'll get a different result than if you're not aware of what's going on.
Right, this
waiting
is
for our lamp to light.
Undoubtedly the hardest experiment this evening for me. There's a famous comment about any experiment that involves the word quantum. If you think you understood the explanation, you weren't listening closely enough. Okay. We saw the Young's double slit experiment. One of the key points about that experiment is that we don't know which slit the light went through. One of the important arguments of quantum mechanics is that if you do know which slit it went through, the experiment should no longer give you the fringes. This is what we are attempting to show you. We've reset up the Young's double slit, and if we look on the handheld camera, what I've done is I have placed 2 pieces of Polaroid, one in front of each slit. The right-hand slit, the Polaroid is polarizing the light at 45 degrees to the right, and the left-hand slit, it is polarizing the light at 45 degrees to the left. We don't know which slit it's going through, but the 2 beams fail to produce a diffraction pattern. If I now place a piece of Polaroid, let's see if I can get it right, vertically polarized, we do not know which slit it went through, and we see the characteristic diffraction pattern. If I take it through to 45 degrees, we now know that the light is coming through the right-hand slit, and the diffraction pattern goes away. If I take it back to being vertically polarized, we don't know which slit it went through and it comes back. If I take it to 45 degrees to the left, and I've almost killed the light so the poor camera can hardly see, the diffraction pattern disappears. This is a very simple, and there are much, much more complex, much more delicate tests, where if you do the Young's double slit experiment, but you have some method of knowing which slit the light went through, the diffraction pattern is destroyed. I recently helped Jim Al-Khalili do a pair of programs on BBC 4 about quantum mechanics, and unquestionably, the point that came out is that Young's double slit experiment, the issue over the nature of light, 200 years after Fresnel thought about it, remains an absolutely active branch of science. Quantum mechanics, which has had to be introduced to it, allows us to do experiments today which are on the very, very edge of understandability. And it still remains something that science is studying.
So if you fire particles of light as opposed to waves of light, they behave the same. That's what they're finding. And only last week, literally last Tuesday week, a photograph was taken of light behaving like particles and of waves at the same time. So far from being an old experiment, this is totally current. And Lord Rutherford said, anyone that thinks that they understand quantum mechanics doesn't really, because it's quite baffling as to why a particle, if you know which way it's going, won't do an interference pattern. If you don't know where it's going, it will produce it. There's two main things I'd like to say before I finish. All the way through this talk, there's been an elephant in the room, and that's been the Fresnel lens. Everyone's heard of a Fresnel lens, and so far I haven't even mentioned it. When I was at school, I first got paid for doing some lighting when I was 8. I used to have a Saturday job passing lamps up to people in a dance hall, and I came across these lenses then. And then when I was 15 and we learned science and art, I asked my physics teacher, when we learnt about refraction and diffraction and things, was this the same Fresnel? I think it was the first rhetorical question I'd ever asked. And he said that it was. And from ever since that point, I just found that if you go with what he teaches you when you're lighting something, you can't go far wrong. And I'm very pleased to say that his wife and his son are in the audience tonight. Now, when you're doing lighting design, you can do it on a very, very technical basis, and you can do it innately in an artistic way, and sometimes it's a mixture of the two. Sometimes you have to measure luminance and illuminance. You have to do lots of calculations and sight measurements. And sometimes it's just throwing a piece of light at something and just knowing it's going to work. And experience is the art of knowing what to consider. And what Fresnel does, if you need to do it in the technical way, he will tell you where to go, how to go about it. But if you don't, I mean, artists for thousands of years have just been painting by looking at things, and all of this is built into our psyche. Okay, now if we look at a standard lens, what Fresnel did was to cut the thing up like this. So he was he's very, very good at studying physics. But when he was in 1821, lots of mariners used to get drowned at sea because their vessels hit the rocks and their lighthouses weren't very good. And so even though he had very ailing, failing health and he had just produced all this other work, he was asked to look at this as a sort of an odd job. And him and his brother Fulgence continue this to the end of his life 6 years later. What he did, he took this lens and he broke it into subparts. And we can analyse these. You can either make a Fresnel lens produce a parallel beam of light, like you would in a lighthouse or in an underground station as a signal. Or you can make the prism slightly differently and produce a different beam where it all comes to a point, so you're actually just using it in reverse, which you might do if you're trying to make paint, high temperature paint dry or something in a car factory. But this is known as a negative Fresnel lens, not a positive one, like it said. And it makes the beam diverge, which is what they used in stage lighting. So this stage lighting then makes the light, it gives a soft edge beam, okay? And I don't know, there's probably about a third of the people here are stage lighting designers. And this is a Cutaway 223. And I wonder how many people here have actually grown up with these. If there was a top 20 most important light fittings of all time, with the angle poise being one of them, say, even if you've never used one because they're only used in theatres, the 123 and the 23, which we'll be talking about later on because there's going to be a competition about them, has been one of those important lanterns. And if you were on the underground, you'll actually see the circles of light when you're close up. And from a distance, they look much, much brighter. So if you're on a curved station like Bank, without falling into the rails, you can actually see into the beam. So it's quite brighter. Yes, normally if you're giving a talk, you don't use terms like blue skies thinking or outside the box or any of those cliches. Slightly further down on the list is the Rosetta Stone. You know, this is the Rosetta Stone of something. But in this case, I think I'm justified because indirectly the Rosetta Stone says something about Fresnel's character. It's 3 languages that were found on this tablet, and one of them was hieroglyphics. And Thomas Young, who became a corresponding friend of Fresnel, was a polymath. In this book, The Last Man Who Knew Everything, he was so called because historians don't tend to write about polymaths. They think that Leonardo da Vinci was the only one that ever existed. And he invented he discovered Young's modulus with the stretching of metals. He invented the idea of insurance. He did this 2 slit experiments. And one of the things he did, he was the first to translate hieroglyphics. And what he did, and this is relevant to Fresnel, he looked at a thing called a cartouche, which is a name of a pharaoh on the stone. And by studying the name, he managed to work out what some of the letters meant. But he told Champollion, and Champollion ran with the idea, and he's the only one that anyone remembers for translating hieroglyphics. And they never spoke to each other again because he didn't credit them at all. Whereas Fresnel and Young didn't always agree with each other. They did disagree and agree, but they did correspond. And towards the end of his life, because Fresnel died very young of TB, he was only 39, Thomas Young made sure that he won the Rumford Medal, which was the equivalent of a Nobel Prize at the time. And he received it just 1 week before he died. It was taken to him. So he got the accolade at the time, which was good. So that shows that he was the kind of person who, if you take two things about him, if you take the so-called Fresnel lens, because he designed many types, and in terms of his popularity, not his legacy, if this was his #1 selling 12-inch single, then his work on reflection, refraction, interference, double refraction, polarization were his critical albums. And lastly, this correspondence, we live in a modern internet world. The World Wide Web has only been around for since 1991. And this way in which people from all over the world who may not speak each other's language very well, Fresnel didn't speak very good English. When he was upset that when he thought he had missed the boat about this experiment early on, his friend Arajo used to translate between the two of them, and they used to correspond and try and make the world a better place. And I think that attitude is timeless. Thank you very much.